Here's problem 2 on sample test 2. Three masses are connected on the table as shown on the right. The table has a coefficient of sliding friction of 0.3. The three masses are 3 kilograms, 2 kilograms, and 6 kilograms respectively, and the pulleys are frictionless. Determine the acceleration of each block and their directions. What is the tension in each cord? And if the masses start from rest, what is the velocity of the 3 kilogram mass after 2 seconds? Alright, to look at this, first thing we want to do is make a free body diagram. And in particular, if we're looking for acceleration, let's blob the whole thing together so we don't have to worry about tensions at this moment. So we're going to choose a system that contains all three masses. And since the mass 3, which is 6 kilograms, is larger than mass 1, which is 3 kilograms, we have a very good idea that this system is going to move in a forward direction like this. So the acceleration will be in that direction, in a forward direction. Making it go at the front is going to be a force equal to m3g. Making it slow down at the back will be a force equal to m1g. Up here on the table we have a m2g, but that's going to be transverse to the motion. It's not going to contribute to the acceleration because it's perpendicular to the actual motion on that table. Also, we're going to have a normal force, which is also transverse to the motion. It won't contribute to the acceleration either. However, we are going to have a frictional force against the motion on this table, equal to mu times the normal force. And that frictional force, which is mu times the normal force on that table, the normal force is going to equal the weight because we have these two forces canceling out. So this frictional force is going to equal mu times m2g. Not the whole mass, but just it's only acting on mass 2, so it's mu m2g. Alright, so if I were to set up Newton's second law for what's going on with this blob as it moves in a positive direction of acceleration, I would say that the summation of all the forces in that direction is equal to the total mass, mass 1 plus mass 2 plus mass 3, times acceleration. And that is equal to the net force in the direction of acceleration. This will be m3g minus m1g, which is working against it, minus the force of friction, which we just determined to be mu m2g. So if I solve this for acceleration, I would have acceleration is equal to m3 minus mass 1 minus mu mass 2 all times g divided by the total mass, m1 plus m2 plus m3. So this is equal to 6 kilograms minus 3 kilograms minus 0.3 times 2 kilograms, all that, times 9.8, divided by mass 1, 3, plus mass 2, 2, plus mass 3, 6. If I figure this out, I have 6 minus 3 minus 0.3 times 2 times 9.8 divided by 11. I get 2.14 meters per second squared. That's the acceleration for all three blocks. In particular, the acceleration will be up for mass number 1, to the right for mass number 2, and down for mass number 3. But it will be in the direction as we've indicated for the acceleration. Okay, so now we found the acceleration. We want to find the tensions in each of the blocks and their directions. So let's do a free body diagram of mass 1. We're focusing on mass 1, which is 3 kilograms. And we're going to label all the external forces acting on it. Well, it's got weight equal to m1g pulling down towards the center of the Earth. And then there's a tension force in this first cable. Let's call it T1. And as a result of these two forces, mass 1 manages to accelerate up with a value of 2.14 meters per second squared. So this would be our free body diagram for mass number 1. If I were to set up Newton's second law for this mass, I would say that the m mass 1 times a is equal to the net force in the direction of acceleration. Positive acceleration going up means I will have T1 minus m1g. m1g is in the opposite direction. Hence, tension 1 is going to equal mass 1 times acceleration plus mass 1 times g. So this is going to be 3 times 2.14 plus 9.8, and that is equal to 35.8 newtons. So that is tension number 1 in the cord. Suppose we want to find tension 2 in the other cord. Let's do a free body diagram of mass 3, which is also hanging. Mass 3 is 6 kilograms. And if I were to label the external forces acting on it, I would have a m3g pulling down towards the center of the Earth and a tension 2 pulling up inward on the cord. As a result of these two forces, it manages to accelerate down with a value of 2.14 meters per second squared. So this would be my free body diagram for mass 3. If I were to set up Newton's second law based on this, I would say that the summation of all the forces in the y direction is equal to m3a, and that is equal to m3g minus tension 2. So I would say that tension 2 is equal to m3g minus m3a. That's going to equal 6 times 9.8 minus 2.14, and that is equal to 46.0 newtons. So that is the tension in the cord 2. And that's our answer for part B. For part C, it says if the masses start from rest, what is the velocity of the 3 kilogram mass after 2 seconds? Well, this is just a straightforward kinematic problem, and we know that the acceleration of all the masses are going to be 2.14 meters per second squared. We're going to start from rest. Our initial velocity is 0, and our time is going to be 2 seconds. So we want to find what is the final velocity. This looks like kinematic equation number 1, where final velocity equals initial velocity plus acceleration times time. In this case, the initial velocity is going to be 0, and so our final velocity is going to equal acceleration 2.14 times time 2, or 4.28 meters per second. That will be the final velocity of the whole system, and that will also be the final velocity, in particular, of the 3 kilogram mass after 2 seconds, and it will be going up when it's doing so. So this is the answer to part C of problem number 2.